Hello, everyone, and welcome to Cloud Native Live for May 28th, 2024. I'm Taylor Thomas, and I'm your host for today. At Cloud Native Live, we take the time to go around and look at the cloud native technologies and see how it's actually used. And so it is a CNCF event, and as such, it is governed by the CNCF Code of Conduct. Please keep your comments and interactions civil and kind to others, and we hope to have a great stream. So today we're going to be learning about some advanced Kubernetes with Dan Norris. And so I will let him introduce himself, and we'll go ahead and get kicked off.
Hey everyone, great to be here. My name is Dan Norris. I'm the infrastructure lead over at a company called Cosmonic, and I'm here to talk to everyone today about advanced Kubernetes integrations with wasmCloud. So before we get started, figured I would, if I could actually focus my screen, go through the agenda real quick. So what I'm planning on doing is probably giving everyone just a basis of understanding of sort of what WebAssembly is, since that's what wasmCloud, the project, is all about. You can tell by the name. And then a brief introduction to wasmCloud. And then we'll get into the Kubernetes side of things, right? That'll give everyone kind of just a common understanding before I go too far into depth. And then we'll talk about what it is like to write a Kubernetes operator in Rust. We'll talk about specifically the wasmCloud Kubernetes operator, which is open source, part of the wasmCloud project. We'll talk specifically about some of the stuff that we had to work on to actually enable that, specifically API aggregation and also the API discovery features. We'll also talk about endpoint slices, which are kind of an advanced Kubernetes feature for actually coordinating, orchestrating service endpoints. And then I'll give a couple of demos about what all this kind of looks like and how it all fits together. So with that, I'll jump right in. So in case you haven't heard of WebAssembly, normally, like when I give like a talk in front of a crowd, this is where I go like, show of hands, who've heard of this, right? But in case you haven't heard of it, WebAssembly is something that originally came out of the browser. The idea was to be able to kind of get near or close to near native performance for applications running in a browser context, speed them up, just kind of get rid of some of that JavaScript and make it all faster. But as sort of that technology has evolved, more people have started looking into it. It started to find some use cases more on the server side, actually. Reason being is it's kind of like, if you think about it, a really lightweight container. And we'll go into specifics as to what that means in a second. But what we, both as a company and also as the open source project wasmCloud, think of this of WebAssembly is we really see this kind of like the next stage of evolution for platform engineering. Before, like in the before times, if you will, right, when all we had were basically bare metal machines. We just had computers that were sitting in some racks, maybe if you were lucky. And poor sysadmins had to sit there and like manually sit there, type that all out by hand, right? There are these bespoke machines. And then the virtual machine revolution came around, right? Where the idea, going back to sort of like the mainframe days of like, what if I took this machine and partitioned it so that I could take better advantage of the resources there, hence VMs. But then, that all worked. We had clouds, we had VMware, all this technology, right? But then we realized that deploying those applications and sort of having applications and managing things at sort of like data center or cloud scale was really difficult. So then Kubernetes came along, right? And the real innovation there was wrapping, some other components, namely containers, right? So C groups and namespaces, packaging all that up nicely, and then orchestrating them across various machines on top of virtual machines, like I said. So the way that we see that evolving, right, is like that's all great for infrastructure, but what about for applications, right? Kubernetes at its core is really, really good at orchestrating infrastructure, right? So, moving workloads around and making sure that your nodes are up and have a consistent API. And we see the kind of next revolution as taking your applications and being able to sort of orchestrate those in the same way in like a platform or a architecture or a infrastructure agnostic manner, so hence WebAssembly. So you can think of WebAssembly as kind of like a tiny virtual machine, because that's literally what it is. It's actually virtual machine implementation in bytecode. And the idea is basically you can write code in any language, package it up into what's known as a WASM module, which is compiled to bytecode. You can run that in theory, any runtime, which will run on any supported architecture. For those of us who have been in the industry for a little while, you might be thinking to yourself, well, haven't we tried this before? Wasn't that what the JVM promised me and what the CLR promised me and everything like that? And that's pretty true, right? The difference this time around is pretty much all the major languages support WebAssembly in some way, shape, or form, and that support is actually continually evolving. So it's from the get-go, it has a lot more the cross-language buy-in than something like the JVM had. And the name's a little bit of a misnomer, right? It's neither web or assembly, at least in the context that we're talking about, right? And it is at its core, it is a open W3C standard. So there's a whole committee basically in charge of sort of making sure that all moves forward. There's also a open source industry alliance called the Bytecode Alliance that shepherds all the standards. The other key difference between this and some other attempts at sort of like this virtual machine bytecode native deployment mechanism of applications, it is that it's just because it was designed for the browser, it's secure and sandboxed out of the box. So WebAssembly components can only access things that you tell it to, and that's it. It's all capability driven. It's efficient and fast. They're pretty small. Like I've compiled WebAssembly modules that are like 80 kilobytes in size, which is pretty different compared to say Docker containers, which can be upwards of like, I don't know, 40 to 50 meg if you're doing like a Go binary. I've seen containers range all the way up to multiple gigs, right, depending on what you're doing. We talked about polyglot. It's nice to be able to write this stuff in different languages. And it's hosted, again, in most edge and cloud orchestrators and whatnot have support for it in some way, shape, or form. The big innovation and the reason why we're kind of going through some of this stuff is because there is also like a very different way of looking at putting these WebAssembly modules together, and it's called components. And so components are kind of like wrap these WebAssembly modules and provide you with the ability to sort of import and export interfaces across them. So you can actually kind of link them together and compose these components, if you will, these disparate parts to ship kind of one monolithic binary if you choose, right? They're language interoperable, and it uses an IDL, so you have strictly defined interfaces. What's cool about that is you can basically have these interfaces and these programs that actually may be written in different languages, compiled down to the same format, which is WebAssembly, and then you can actually compose them together into one actual binary. Very different than what we've kind of seen before. Skip all this. And actually, let's skip past this one. What it looks like, and this isn't really WebAssembly talk, so I only kind of wanted to give you all a flavor of what this actually looks like under the hood. And this is actually like a human readable version of WebAssembly bytecode on the left. And what you can see is that there's various parts, right? Like logging, you can see there's some imports and we export some things, right? That actually allows this WASM module to sort of consume that. We then have a main like we would in anything else, right? Which is where our actual application logic lives, and it's able to consume the things that it's importing. And then it also exports an interface so that other modules, or other components, I should say, are actually able to consume what this actual module effectively produces. So that was a bit of a whirlwind. Definitely feel free to leave questions in chat. But you might be wondering yourself, and I certainly was, kind of looking at this space before I got involved with the wasmCloud project. And the question is, how do you deploy any of this stuff? Like, we have solutions and plenty of them for containers, but like WebAssembly is kind of different, right? How do I manage that? Well, do I have an answer for you? And the answer, in my opinion, is the wasmCloud project, which is a cloud-native project, hopefully soon to be incubating. We've applied for it. And the way that we look at it is a universal application platform. So think of it like the Kubernetes orchestration layer that WebAssembly hasn't had up till now. The intent is to leverage all these components that I just talked about, right, to build more maintainable, scalable software that you can deploy to basically any device, any cloud, anywhere you want, right? Because we have those abstractions. And so what it is really like an orchestration layer for WebAssembly components that's built out or rather its communication layer is built out on another CNCF project called NATS. And what it allows you to do is kind of interconnect on the network and abstract that so that various components can call one another and call various capabilities. And they don't have to know the names of anything. They don't have to know like DNS or anything, right? NATS just kind of helps you figure out where all that is to build kind of like this compute lattice, if you will, as opposed to like a service mesh. It's a fun riff on that language. But it's cloud, edge, and platform agnostic. And you can build in, because of all the capabilities that we have from these WASM components, right? We can extend what those components are able to do at runtime. So for example, if you want to connect to a database, you want to connect to Postgres or Cassandra, or you want to make HTTP calls, right? A lot of that is actually supported out of the box, particularly like the SQL and the HTTP parts, but you can actually layer on all of your own stuff, right? So, there's like, you can define like it's all interface driven. So there's like a key value interface that you can implement, for example, for like Dynamo if you need it, and then deploy it in wasmCloud and stuff. Everything can take advantage of that capability, right? And you don't need to change any of the core logic in your component to be able to take advantage of that. And we got a lot of benefits out of sort of this kind of runtime approach of being able to interconnect everything with NATS. We can basically have like automatic load balancing for your applications because they're just kind of listening on subjects. And again, this is a CNCF project. We've got a pretty active community, right? We've got a wasmCloud Slack that I definitely invite you all to join if you're interested. And we use a lot of other CNCF projects and open source technology to build all this stuff. And so the way that we see, and why we're sort of going through all this pain, right? So you just a touch more on WebAssembly before I keep going forward. Is the idea is basically that WebAssembly, we can build things faster with less code for less cost, and it will make your administration of your applications and maintenance a lot simpler. And so the purpose of this talk, right, in particular, right, and in this whole stream is to talk specifically about how we as a project have integrated wasmCloud and bringing the power of WebAssembly to Kubernetes in particular, right? The way that we see it is that Kubernetes is brilliant at orchestrating infrastructure, right? We spent countless amount of hours, deploying that and getting it to work really well and be able to solve a lot of core problems at scale for infrastructure. But we can see that there's a real niche for WebAssembly to actually be like more of that application layer on top of Kubernetes. I think there's a lot of different solutions out there, but we think this one's a pretty good one. So let's dive into that. So the way that we do our integration primarily is that we have a operator, and so what this operator does, it has a couple of key rules, right? wasmCloud applications and WASM in general, right? You can't really just like run them. They're not like binaries. You can kind of just like, /run binary in a shell or something. I mean, you can if you build it correctly, but because it's sort of bytecode, you need a virtual machine or a application or a runtime, I should say, to run them. So in our parlance, we call that a wasmCloud host. You can think of it as our equivalent of a kubelet. So it's the program that actually is sitting there waiting for commands, start a component, run it, scale it, right? Take in requests and handle them in a component. We call those hosts, and those need to deploy somewhere, right? This operator lets you define how you deploy those hosts using a CRD, right, that it understands, that effectively orchestrates, a deployment of all these hosts that are kind of like related. The other thing that it also does is we have, because I spent a lot of time talking about components, right? Or rather applications. These applications need to be described somehow, right? We opted to use a model called the Open Application Model, or OAM. And so we'll look at what that looks like in a little bit. But what that is a YAML manifest describes how all of your components fit together, and kind of what makes up an actual application is a deployable unit. And then we can schedule that using actually another piece of software called Watum, which is kind of like our WASM native orchestrator. And that basically allows it to manage the lifecycle of those applications. The operator understands how to integrate that natively, and we'll talk about why. Spoiler alert, it's called aggregated APIs. The third thing that it also does is manage the ability to generate services and actually provision them for you. So for example, applications are pretty useless unless you can drive traffic to them, right? The whole point of this is you're supposed to build an application that is receiving requests and probably giving out response, more than likely by HTTP. So because we know and we have like a YAML description of what's going on, we can auto-generate Kubernetes services so that you can advertise that back to your existing applications to be able to interact with these WebAssembly applications as if they were anything else, right? So we can do that seamlessly, and the operator is intelligent enough to do that. If you're interested and you want to follow along with some of the code, because we're going to walk through it in a little bit, the code is at github.com/wasmcloud/wasmcloud-operator. You can see that at the bottom of the slide. And so I did mention that the first thing that this does is that it manages hosts using a CRD, custom resource, right? And you can see what this looks like actually over on the right-hand side of the screen. And the idea here is to provide that Kubernetes native experience for actually running and provisioning these hosts using Kubernetes primitives, which is basically just a deployment, right? And so if you look at this, right, and you're familiar with the way that CRDs sort of fit together and have run them before on Kubernetes, right, this shouldn't look totally alien to you, right? So we have an API version, which in this case is kubernetes.wasmcloud.dev/v1alpha1. Its kind is a wasmCloud host configuration or config. It has a name called a Cloud Native Live, since that's where we happen to be at the moment. In this case, we say up front, we want to run 2 replicas of these hosts. We say what lattice it belongs to, which is effectively you think of it as a Kubernetes namespace, same idea. We can give those hosts a bunch of labels similar to what you would do in Kubernetes. We say what version of the host we want to run, and then if it needs any secrets to talk to, say, a Nets backend or, to interact with like various cluster issuers, which are like a pretty advanced topic I'm not going to get into. You can define all those there, right? And so the idea here is to allow DevOps teams or infrastructure teams or platform teams, however you want to kind of think of them, to be able to own and manage deploying these hosts as alongside any of their other infrastructure, right? As if they were just another pod, right? You can the CRD, which I'm not showing, exposes pretty much all of the pod scheduling options. So you can have them run in particular nodes, right, that are identified by selectors, all that good stuff, right? And so you can use all of the same tooling that already exists, right? You can deploy this through Argo. You can just use kubectl to own and manage your infrastructure like you would anything else. And you can kind of automate moving across versions and kind of manage them, again, like you would any other application. So the other thing that this does is orchestrate these wasmCloud applications, right, using OAM, which is the Open Application Model. And you can see an example of this on the right-hand side, and I'll bring up another example of this as well later. But if you look at this, right, this looks, again, very similar to other types of CRDs that you may have seen before, right? In this case, the API version is OAM. And its kind is an application, right? We give it a name, some annotations. And the annotations, really the only big thing you're going to notice, version, so we have semantic versioning support. And then it has a list of components. These components are WebAssembly components, right? So they're little bits of deployable platform agnostic code, right, that we can kind of put anywhere. And they can be pulled from OCI registries, which in this case you can see here under that properties, that image. That's just an OCI reference to a pre-built WebAssembly binary, right? And then we can say where we actually want to schedule that, right? So we can say that we want to spread that component kind of anywhere where it's going to run, and we want to be able to run at a max concurrency. It's actually what replicas means in this case, of about 5,000. So at max, we want 5,000 of them to be running at any given time. Why is that important? In the wasmCloud model, we actually run things to completion. So when a component handles a request, it starts up, handles it, spins down, and will instantiate from memory then on out, right? A little bit more fuzzy or serverless in that way. But not to say that you can't write long-running and complex applications, but that's sort of like the default runtime model. So being able to clamp down on your concurrency lets you build resilient applications because you can fan that in and out depending on how many requests you know you need to handle. And in wasmCloud, and particularly with the component model, I mentioned that you have like everything, you have to grant permissions to be able to call out for external things, right? We call those capabilities. So this is all capability driven. That's block number 2 in this diagram. We're declaring upfront that we have this particular component, which all it's really doing, by the way, is it receives a request and gives you an echo. So whatever you parameters you give it, it'll kind of spit you that back out by HTTP. But anyway, in order to do that, you have to have a web server, right? And so what this is saying is basically, I want to link this to a capability, which is the HTTP server, to grant it access to be able to receive HTTP requests on a particular port. And that is defined in block 3 here. You can see it down kind of like most of the way toward the bottom. There's like properties, address, all interfaces 8080. That's what tells it that, yes, I want you to be able to handle incoming requests on port 8080. And the third thing that this operator does, and again, we'll look at this in a lot more depth once I kind of get into the code and talk a little bit more about the architecture of the operator, is actually to provision services on your behalf. So that example that I showed you before, right, it's listening on port 8080. Well, you probably want to drive traffic there if you're listening on that port, right? And in Kubernetes, the way that you do that is you create a service, right? And you use one of the many ways to expose that service to the wider internet or to whatever happens to be ingressing your traffic. And so since that's kind of the primitive that we're working with, the operator will actually spin these things up for you. And so the service, because it has a finalizer, right? Basically, what that means is that the actual control loop that is running the operator owns this particular service. So if you try and delete it, right, the operator basically has final say as to whether or not it's deleted or if it needs to clean it up, right? That's what finalizers largely do. I'm hand waving, but that's basically what it is. And so the name is automatically generated basically based on the application name, and then everything else is sort of figured out from there. The key difference here is and we'll get into this in a little bit once I start talking more about endpoint slices, but services actually create endpoints or endpoint slices typically under the hood. Our operator actually manages that for you. And basically that's what actually does all the nitty-gritty networking bits behind the scenes in Kubernetes. It's what registers effectively your pods, right? They're just lists of endpoints that service sort of wraps. And so we actually do that for you. And there's a couple different reasons why we go that direction. I'll get into that. But that's kind of like a little bit of peeking under the covers of what a service sort of does under the hood. But wait, I did mention Rust, right? That was sort of something I kind of teased on in the beginning, right? And so the thing about our operator, which is a little different than what you may have seen in the past if you've looked at other controllers or operators, is that it is 100% written in Rust. We actually use another CNCF project called Kubernetes, which is a library that basically implements a Rust equivalent of like client Go, which is the Go SDK for Kubernetes, in a more generic fashion, because Rust gives us like better generics than the Go language does. And what's nice about it is it has its own controller runtime abstraction, kind of like KubeBuilder, but you don't actually have to like auto-generate a bunch of stuff. And it also lets you manage CRDs, in this case using macros instead of code generation, even though it's kind of all code generation if you think about it. And so we did this for a reason, and the reason was primarily because wasmCloud itself is written in Rust. which allowed us to reuse a bunch of the libraries that we kind of already have in the ecosystem. And as someone who's spent quite a bit of my career, the last, like, I don't know, 6, 7 years, writing controllers and operators and whatnot in Go, the QRS actually gives you really nice abstractions, and I find it much easier to build out controllers in Rust. The patterns are just easier to work with. There's a lot, like, it's just less boilerplate in a lot of ways compared to something like QBuilder. So we decided to kind of go in that direction. And again, we'll get into the code in a little bit to kind of give you a bit of a flavor of what this looks like. There were some rough parts, of course, right? Particularly when you're sort of going a little bit off the beaten path. And so the things that we discovered in particular, right, about this that you may not have run into or probably will never have to run into unless you're really deep in the weeds and possibly even just a Kubernetes developer, is that we discovered that one of the primary features that we wanted to enable for was integrating Argo. So being able to say, take one of those WASM manifests and deploy that using GitOps using Argo. What we discovered was that Argo only uses OpenAPI v2, which is supported in Kubernetes to describe the spec of a CRD. They only support that. Kubernetes is supports both v2 and v3. They're biasing toward v3, but it's kind of unknown as to when v2 support will be deprecated, at least the last time I looked. The problem is Rust has already moved on to the future, right? They're like, why would you ever use OpenAPI v3? Why would you even bother? Unfortunately, that's kind of hard when you actually have to have those schemas. So we had to actually implement all of that and basically kind of run a translation and kind of have just like a fixed JSON scheme for that OpenAPI manifest. Fortunately, that's like a fairly well set spec. We won't really have to change it very often, but that was a big sort of like face plant real hard into a wall in terms of the implementation here. And we also needed to implement some types and endpoints to use the aggregated discovery features that have come in Kubernetes. They GA'd, I want to say, in 1.2.7, I believe. I think they were beta before that. I could be wrong. If I'm wrong, let me know in the chat. But I'm pretty sure that's what it was. So that's important because you want the whole reason that these APIs are using OpenAPI for CRDs is because not everything knows the schema or the shape of CRDs within Kubernetes itself, right? So schema lets you actually do the right thing and consume these CRDs and APIs correctly without having to sort of infer or guess. So that API aggregated discovery makes that a lot easier, and we'll show you what that looks like in a little bit. Let's see. Before I move on, I see one question. Someone asked if I could detail the security features of wasmCloud that make it distinct from other microservices platforms. Explain how these features improve application security. I can go into a whole talk about this, so I'm just going to give you sort of the high level. The big difference, right, is that wasmCloud, and because of the component model, is entirely capability driven. So capabilities, you may have seen them occasionally, if you're in Docker and you're like, oh, there's a default set of Linux capabilities. Sometimes you may have to mess with catnet admin or these very obscure looking things. What that means is, and so in Linux, that's all kind of bolted on because none of that was ever really formulated from the get-go, right? You have to opt into capabilities security as opposed to sort of having that be default. wasmCloud only does capability-driven security. So effectively, if you start a component and you don't give it any capabilities, it can do nothing, right? At least when it comes to interacting with the outside world. It will just sit there and run happily and nothing, it will never be able to reach outside of its sandbox. You provide it those hooks by granting it access to capabilities. So HTTP, database access, right? And HTTP is broken up into even client and server, right? And those capabilities are defined through interfaces, very similar to something like Thrift or gRPC, right? I mean, gRPC is what we all use these days, at least for describing interface-driven kind of RPC stuff. So that's the big difference, I would say, between wasmCloud and other microservices frameworks. Because it embraces that so well, and from the get-go, right, you have better application security because, again, you can only do these applications can only do what they tell them to do. The other reason that you may find this interesting is because by breaking up those capabilities, your applications focus just sort of on their business logic and what you want them to do, versus having to worry about the nitty-gritty details of like, oh, hey, I need to configure an HTTP client and it needs to do this, and I better have configured my timeouts. You can offset that. Big example would be something like, very enterprise examples like Log4j. If you decouple your logging framework from your application code, you can just worry about when you have to roll that out of upgrading your logging capability as opposed to having to upgrade every single application because it's just an interface. You're basically making like the equivalent of an RPC call to that, right? So it gives you a lot better tooling. Long-winded answer. I'm definitely happy to go into more detail maybe toward the end of the talk, but that's kind of why we think this is really cool. Okay, that aside, let's get back to Kubernetes. So a very advanced feature that you may or may not have run into, depending on, again, how deep you have gotten into the world of actually building and running operators or controllers, is Kubernetes has this notion of API aggregation. They're also called extension API servers, depending on kind of the documentation you're looking into. But what this is basically you can extend Kubernetes APIs with your own APIs to run, alongside the Kube API server. There's it's a newer kind of feature where they've started to kind of like aggregate all at the top levels. So the API server just sort of knows how to handle individual paths. And we'll see what this looks like in a second. I have like some very concrete examples to show you. It's different than just creating a CRD because a CRD is really just like a data type, right? Yes, a controller typically sort of consumes them, but it doesn't. It may just do that sort of using like a reconciliation loop by watching for the type and changes to it. It doesn't actually handle individual paths, and it's important for a couple of different reasons. And I'll get into that in a bit. But what this looks like is you actually register an API service object to handle this particular path. And then Kubernetes knows that when you register that path, it needs to proxy everything related to that type to that path. And in our case, because we kind of have our own orchestration layer going on in addition to Kubernetes, the state of your applications is actually not stored in the cluster. It's stored actually in our NATS layer. And what's cool about that is it means multiple Kubernetes clusters, and we'll show this off in the demo, can reference the same application state, and the operator will sort of roll that out kind of everywhere. So you're not just restricted to having like a Kubernetes cluster. It's kind of your hub, and everything sort of like routes out from that using the Kubernetes data backend. But in order to do that, you have to use API aggregation, and it is one of the reasons why it exists. And I talked about this before, but I wanted to kind of touch on it before I jump over into showing you kind of how this fits together. But we also use endpoint slices directly in the operator. Again, they are typically managed automatically for you by Kubernetes whenever you create a service with a selector. So, again, if you've been doing Kubernetes for a while, you know that whenever you create a service, you typically give it a set of label selectors so that it knows which pods to match in order to drive traffic. There is a control loop in your controller manager, actually, that takes those whenever you create a service and automatically generates a whole bunch of these endpoint slices for that service. They used to also just be called endpoints directly. This is an evolution of the same idea. They did it for a couple of different reasons, mostly because it's more scalable, but also it allowed the developers of Kubernetes to add some newer features that they wanted to do for a long time, namely topology-aware routing, so you can kind of route depending on labels effectively, and also add dual stack support so that pods could have IPv4 and IPv6 addresses, and all of that is actually powered by these endpoint slices. And there's also some other kind of non-intuitive things that you can actually do if you're using endpoint slices directly. Like, for For example, because an endpoint slice is just pointing to pod addresses, you could, in theory, create services that span namespaces if you wanted to. There are reasons where you may or may not want to do that, right? And probably I would err on the side of don't. But there may be reasons to, and there is like a hook to basically have very, very fine-grained control over your networking stack in Kubernetes. So with that, I'm going to jump in to show you kind of what this looks like actually running in just a local cluster, and then also show you kind of a more advanced version of that running in the cloud. So I wanted to give you a sample of kind of what this looks like as a CRD. So this is a bunch of Rust code that defines our the CRD that we actually use to deploy these wasmCloud hosts, right? And it may help if I have this up at the same time, just so you have kind of a reference here, right? This is what it decomposes into in Rust, right? So we declare that we have, this kind or group version kind, just like you would in Kubernetes regularly, right? We get a bit of short name, status. All this is stuff that you kind of get for free with KubeBuilder anyway. The difference is because this is Rust and we have macros at our disposal, right? This is all sort of like automatically generated at compile time, and I don't have to think about it as a developer. And so we have a whole bunch of data here, right, that defines the schema and whatnot. All corresponds over in here. So nothing kind of revolutionary here, but there's some fun stuff that I'm able to do because of the fact that we're using Kubernetes, right? Like we embed effectively all of the pod template additions in a pod spec. Other than being able to add additional containers, there's a whole reason why we opted not to do that. But we actually, so it makes it pretty simple and straightforward to sort of build up CRDs as just sort of like native code Rust structs, and then represent them in YAML, again, just like you would kind of do in KubeBuilder. Other thing I wanted to show off was the controller itself. Apologies. I use NeoVim, by the way. I'm not cool enough to use Visual Studio Code, so hopefully this is all legible and everything's makes sense to everyone.
In case you were doubting Dan's infrastructure engineering credentials, he's using NeoVim for those out there.
Oh yeah, take Vim bindings from my cold dead hands, all that stuff. I will tolerate if you use Emacs. That's a whole other thing. It's fine, right? Anyway, so the main loop of our controller, right, is just this run function. And if you've looked at what client Go gives you, right, which is effectively what KubeBuilder is wrapping and kind of making a little bit more accessible. On the surface, it seems similar, but the actual implementation is quite a bit simpler, I think, than what they give you. So effectively, we are given the ability to create a Kubernetes client. We declare up front all the things that our controller is interested in watching for changes. Reason being that this controller generates a whole bunch of core Kubernetes constructs when it gets a request to create that CRD. I'll show that off live in a little bit. But in this case, we watch over like configs and config maps, and configs being our CRD, deployments, secrets, services, pods. We watch for some services, and then we instantiate a new controller and declare up front that this is how we want to watch them. We want to shut down on a particular signal. We have a reconciliation loop, and if we everything's fine, we sort of say that's fine. If not, we warn about it and we kind of keep going our reconciliation. Our reconciler is this function, right? And we just sort of declare that we have a finalizer that needs to run if and when something ends up being deleted, and we register all of that. So that's surprisingly little code, right, in order to effectively bootstrap what is at its heart a very complicated idea, basically a Kubernetes reconciliation loop on an arbitrary list of Kubernetes constructs that that it just has to register and sort of work with itself. And then within this finalizer, right, we either reconcile it or we clean things up. The other thing that I wanted to show off was services, bounce across over here. Where's our endpoint slice? So this is the code, and again, I'm kind of doing this at a very high level, but this is the code that sort of keeps an eye on our endpoint slices. And so what this does basically is it goes through, and anytime that we see that from our WADM orchestrator that we are creating something that needs a new service endpoint, right? This whole routine sort of kicks off and actually manages all that. And if there are any changes, right, it updates them dynamically, right? We make sure that all of our pod IPs, excuse me, we only do this for pods that are in the running state, and we kind of keep an eye on that. And so as our endpoints kind of spin up and spin down, or pods migrate through the cluster itself and may terminate or whatever, that we're keeping that up to date. So our service is only pointing to live endpoints, right? Other thing I wanted to show off before I go into actually running this stuff live is we have a router, and this is what powers the API aggregation layer. And unfortunately, again, because we're doing this in Rust, we kind of had to reverse engineer some of this just because kubeRS doesn't quite have that support yet. If you're doing all of this in Client Go or in KubeBuilder, right, you get all this stuff for free. You can actually find all of it if you dig hard enough into the code, which is how we were able to replicate it. But this is the stuff that actually gets registered when this controller spins up. It registers all of these various API endpoints specifically used with that aggregation layer that I mentioned. And it actually will handle all of that because what this does is it actually calls out to our WADM API, our other orchestrator API, to integrate with via that application layer. So it's kind of acting as a proxy for another API, and that's why you use this stuff. And so it does kind of what you think it does, right? Like you kind of see this in over in kind of like our get and our post handlers, right? We list applications, or all of them, we list like a filtered list of them, right? We can create them, just get an application spec, patch them, delete them, whatever. All of that is handled through this routing layer. So what this ends up looking like, and we're going to go through, I'm going to bootstrap this real quick on a local kind cluster, just so you can kind of get a flavor of what this is. And then I have another more complicated deploy that I pre-staged, mostly because GK is a little slow at kind of getting some of the routing together. And we'll walk through what all this looks like sort of end to end, so you get a feel for what this is doing and kind of how the pieces actually fit together. So first off, let's sure we're in kind. Oh, it's not even started. So perfect. So I'm going to start a kind cluster real quick. And this is all in the wasmCloud operator repository. So you can follow along if you wanted to kind of like start this stuff up on your own, or you can just watch it. All this is in the README in the repo. So we'll wait for it to come up. Always takes a little bit. Here we go. By the way, just point of order, I have kubectl alias to k. So if I keep forgetting to fully type out kubectl and just type k, know that that's what that is. Muscle memory is what it is, right? So we don't have anything running, right, other than what happens to be started up as part of a regular kind cluster to begin with. Now, what we're going to go ahead and do is go ahead and start this operator. Before I do that, I have to run nats. So I'm just going to helm install it, right, using just a values.yaml that's actually checked into this repo. So let me go ahead and get that going. Here we go. So container is creating, doing its thing. Takes a little bit to sort of get itself together, which is unfortunate. Here we go. In the meantime, well, actually, let me wait for it to actually come up. I was sort of just like assembling. What it's doing is actually getting quorum because it uses Wrapped behind the scenes for all of its storage. So it has to sit there and gossip and do all that sort of stuff. In the meantime, let me show you what we're actually going to deploy, right? So in this repository, right, you can see there's a pile of files. You can Helm install this operator. I'm going to actually just use customize just to build it sort of locally. Same thing, right? I just prefer customize typically. And so what this is it's just going to deploy go base deployment, this wasmCloud operator, right? We're going to just deploy it from GHCR, and it's going to run its own namespace. We're going to bootstrap that namespace, create a service account, pull a bunch of RBAC, right? It's pretty permissive because it runs a cluster scope, so it needs access to a whole bunch of services, config maps, specific secrets, mostly for actually the secrets that it actually needs to start up your hosts. And so that's all just a whole pile of stuff. Let's quit out of that. I can type. Here we go. That's all ready. Before I do that, I'm also going to start up our orchestrator. And I'm just going to cargo run it, mostly because I'm lazy and I have the code all checked out. Normally, you would also install this with a Helm chart onto the cluster, right? This is our wasm scheduler. This is what's actually going to wait for applications that we want to deploy. Wash is the command line for wasmCloud. It's the wash shell, or the wasmCloud shell. Very funny, right? But because I have that WADM binary running, right, this is actually talking directly to it via NATS. And you can see we don't have anything deployed right now. So let me go ahead and start up the operator. Right, we're just going to customize build it, and then Kubernetes apply it based on all of the manifests that we happen to have running in here. Pod and wasmCloud operator. So it's already started, right? It's running in its own namespace. We do that just because it's easier to sort of manage. And so all looks good. It starts up really quickly. The big thing here, API services. If I can type, here we go. This is the API aggregation layer. When this operator starts, it registers an API endpoint to handle everything related to V1 Beta 1 Core OAM dev. That's what I showed off before when we were looking at the code, right? And so if you look at what this is saying, right, API services is a API type, right, represented in Kubernetes. You can see here that all of these are what are known as local, right? And that's because they're either provided from Kubernetes, or you can see here with this V1 Alpha 1 K8s wasmCloud dev, they're just CRD types that don't have a backing API server implementation. And on this server, or on this cluster, the only one that does is the wasmCloud operator. And you can see it's registered in the wasmCloud operator namespace to the wasmCloud operator service, what should actually be satisfying that request. And so if I do kubectl get applications, right, no resources are found. If it didn't know what I was talking about, it would tell me that there's no resource type that it knows about for that. What that means is I can actually use kubectl to manage these WADM manifests directly as if they were anything in Kubernetes, but it's actually all being proxied out to that WADM binary that I'm running in the background. So I'm going to bootstrap just a quick secret that the hosts need in order to run. And then we're going to go ahead and deploy a set of wasmCloud hosts, really just one of them actually, using that CRD that I showed you before. It's in here, right? It's defined. We're just going to run one replica for now with this particular wasmCloud version, and it'll just run. So apply -f sample.yaml. Pod. Here we go. So it's now creating this container, right, which is our one wasmCloud deployment, right? And here we go. It's all running, ready to go. Now, I have too many tabs open. So I showed you this before, but this is an example of what, like a very basic example of what a WADM manifest looks like, right? And again, so we define up front what our components are, what our capabilities that we expect are, and all of that. So if I want to run this now, what's cool about the operator is I can just apply this WADM manifest. And here we go. It creates the application. Now that one's pretty boring. I'm not going to use that one as an example. I'm actually going to switch over to a demo of this running actually on GKE with a live application and give you kind of a sense of what this really looks like to run something like in wasmCloud in an actual cloud. So let me switch my context real quick. We'll go to East, and here we go. I'm going to switch my context to the Cloud Native Live one. Similar to kubectl, right? Watch supports context. They let you talk to different endpoints. So I think set cloud. Here we go. Sorry, how to namespace prefix. Sorry, so it was getting in the way. But anyway, I have two hosts running, right? And these are wasmCloud hosts, and they are actually running on two different Kubernetes clusters, running a specific app, which I'll walk through in a second. So I have one in US East 4, which is on one Kubernetes cluster, and I have another one, which I forgot to relabel, that's running on US West 1, both in GKE clusters, physically distinct regions. Now, you can see this is already running some stuff, right? And similar to Kubernetes, right, we have a whole set of, these are all labels that are applied to the hosts, right? There's key value pairs. So our database val key happens to be running that, and I'll explain why in a second. And a component and a couple of different providers in this particular cluster, and then a component and only two providers down in the second cluster. Okay, so that's kind of what we have running, but let me show you what we've actually deployed. So this is a demo that we have, and the code is actually all open source as well. There's some things that I need to merge into the main branch, but different issue. But anyway, this is running a component that is serving an HTTP endpoint, and its whole point in life is to basically wait for inbound requests and generate a web page after recording some data about the user agent that happens to be calling this component, and then incrementing some counters and displaying all that data back to you as part of that request. And so it's set to run basically anywhere where we have a cloud is GCP label. We also, I forgot I didn't shut down that. I didn't realize that little guy's been sitting there the whole time. Anyway, this is linked to a key value interface, so which happens to be Redis, which is actually Valkey, because it implements the Redis interface. And our component doesn't care because all it's doing is interfacing, or rather consuming that interface. So it doesn't need to know what it's actually talking to, right? And that's all defined through this link. We also have a metadata capability that lets it get information about the instance that it happens to be running on. That is a capability because, again, components are sandboxed. They can't do anything, like they can't read environment variables or make HTTP calls unless you explicitly grant them access to it. So this capability sort of does all that hard work for the provider. So all it has to do is like call get, and then it's done. We then link it to an HTTP server, which is listening on 8080 again. And then we actually instantiate the capability. So in this case, it's running somewhere that has a label database Valkey. And then we run the metadata provider everywhere where the cloud is GCP. So to show you a little bit more about what this looks like, let me quit out of this. So this is attached to our US East cluster. And you can see we're running just one host. It's been running for a little while, right? We're also running our Valkey stateful set, right? That happens to be serving this particular key value interface. If I get the list of services, you can see two things. One, well, actually, there's this, which actually powers our multi-region ingress stuff. I'm not going to talk about it. It's a GKE feature. They let you do any cast BGP ingressing across all of their cloud, basically. There's some magic part of GKE that lets you implement that. That's how we're going to receive requests from the internet as part of the app, but that's not what the operator does. The operator actually generated this thing called the resiliency demo because that's the name of our application. Like if I do kubectl get applications, if I could spell, here we go. Right, this is our WADA manifest I just showed you. Like it's the actual wasmCloud application running. And so it created a service for that. So if I do resiliency demo, YAML, you can see, like just like I outlined before, there is, where's the finalizer? It's in here somewhere. I don't know where it went. But anyway, this is all automatically generated. Oh, I think it's at the bottom. Oh, that's the application, my bad. That's why I was like, where is it? So what happens when you do things live? Anyway, so this is our service, right? This was automatically generated through our operator, right? Which is why it has the operator finalizer on it, right? You can see it's pointing to a particular pod and cluster IP, and it's listing on 8080, injecting traffic to 8080. But we also do a few more things, right, with endpoint slices. If I get the list of endpoint slices, we can see the resiliency demo again, right? It doesn't have this randomly generated suffix on the end because it was generated by our operator. If I do this, YAML again. And you can see that we applied a whole bunch of labels identifying that the operator is actually what owns this particular resource and is in charge of managing it and cleaning it all up. So what this looks like live is over here. That looks awful full screen. There we go. This is the actual application running live in USC Sport, right? If I sit here, I can refresh the page a couple times. You can see a bunch of counters, increment. Because it's spanned over multiple endpoints, they happen to be in different regions, right? Occasionally one will bounce to the other region because it sees that the component's kind of busy in the first region, so that's why you kind of get mixed levels of counters, right? But what's cool is if I actually switch contexts again, whoops, wrong place. I'm in, whoops, too many windows. Here we go. If I actually go over to my West cluster, I can actually if I delete this, WHC is a short form for the wasmCloud host config. If I just delete it, there we go. If I just straight up turn that off, right? If I do get hosts, there we go. I only have one host now, right? Because I basically shut off my entire US West cluster. Now, if I go over to my app, start refreshing it, see how the counters are only incrementing in US East? That's part of the power of wasmCloud, right? Is to be able to have that seamless resiliency across whatever infrastructure you happen to have running. I mean, the ingressing part obviously was handled by GKE, but if you know how to anycast BGP, right, you can kind of replicate that front end bit. The real important parts are the fact that, if I had, say, this, I could have this application deployed, across regions, across clouds. Like I've run this in this exact same demo in fly.io. It all just sort of fits together, and that's sort of where we end up getting the magic of WebAssembly and sort of this approach to be able to sort of manage microservices and applications using wasmCloud. With that, that's pretty much all I had prepared. So I don't know if we have any more questions on the stream. I'm not seeing any.
Nope, I don't see any more questions. Where can people go if they have more questions for you, or if they want to ask more questions about the presentation, or where can they reach you, Dan?
Yeah, of course. So first off, one of your best resources is going to be wasmcloud.com. That's where all the documentation is for the project. Another great resource to sort of talk about all this stuff in more depth is the wasmCloud Slack channel. We run one, kind of as a benefit for the project. All the maintainers end up hanging out there. We love to talk about technology in general, but particularly WebAssembly, wasmCloud, Kubernetes, all are welcome, right? So definitely come in there. If you do end up giving all this stuff a try, like I think we linked out to the operator repository and the wasmCloud project potentially. If you end up kind of kicking the tires on the stuff, please file issues, right? We love to hear the feedback and to actually, fix any issues as they come up.
Awesome. Well, thank you so much for coming today, Dan, and showing off this awesome technology stuff and learning more about Kubernetes. We will continue, obviously, with Cloud Native Live over the next few weeks. We have a bunch scheduled, so please come back for the next one. And thanks again.